module from the NI instrument here. Okay. So, but right now I just use the 60,000 for the teaching purpose. But somehow this kind of the module I use the level in my another course. Okay, for the data acquisition. So maybe I don't know. Some of my friends will going back in this summer, or otherwise you can choose the level, okay, course. Okay, so for this kind of the data acquisition, okay, you need to install the level first. Okay, so here I would like to show you a very quick demonstration regarding the USB 6000. No, they use the NXG. Oh, sorry. Have you ever heard the level before? No? No? This is a graphic program. So later maybe I can show you. Take a lot of time. Okay, here I think I have a very quick demonstration first of this USB data acquisition device. Okay. No response. Okay. So here, this is the also A channel of the data acquisition for the analog input, and also of the sum of the digital input. Okay. So for the analog input up here, you can find. I just click. So this is the signal. You can see, but right now I didn't put connect to the any kind of the sensor, but here I just put the battery. So maybe later you will find the battery is about 1.5. So here you can find this is the fully charged battery up to the about the 4.6 volt. Okay, so this is the DAQ. Capture the analog signal into the digital one and show on your computer for the data storage. Okay. So here you can find the resolution up to the 4 digit of the precision of the, okay. And right now is the maybe range from the 1.607 to the 1.613. Okay. So this kind of the variation because of the noise from the analog to the digital. Okay. So I just unplug and go back to the to the 0. Okay. So here it is very simple idea of the data acquisition using this kind of the USB. Okay, and because some of you never see the lab view before, so I just quickly show you what is the lab view. So maybe. So lab view provide a virtual interface. Okay, so this is a virtual interface. You can build your own button, like the Visual Basic. And also we have the program, what we call the data flow. So you don't need any kind of the text program anymore. This is the graphic program, okay? Or something like this, using a line icon for the program. So if you have the further interest, please you can have the other course of the lab view. Okay, also in this semester. Okay, I just have a quick example for you of the lab view. Okay, so maybe in my midterm exam, I will ask all of you maybe the same questions. If I have the purpose of the monitoring the earthquake, maybe I will list 3 or 4 DAQ, and you need to choose the better one for your project and explain why. Okay, so I think this is a very typical and very practical issue if you are engineer in the future. Okay. Any questions regarding the signal processing and the data acquisition? Okay. If no, I think we are going to have the third part. I would like to remind you again, our midterm exam will also include the third part, the data interpretation. But here, I think we will have a very good example for you to understand what is the data interpretation. Okay, because right now you have a capability from the sensor knowledge. Which kind of the sensor you need to use? Maybe you need to measure the temperature. You need to measure the water level. So you can choose a better one sensor for the monitoring. And part 2, you already know that if I have some of the requirement for the sampling, okay, you need to know that the Nyquist the frequency theory and also the 3R to choose your hardware of the data acquisition, right? So supposedly, I think all of you have a capability of the sensor and the data acquisition. But however, all the project, all the hardware you already installed for the monitoring, and now you have the several data, I mean the time history data from the monitoring. So how can you interpret this kind of the data for some of the pattern, maybe the landslide, or maybe the leakage of the reservoir or some of the subsidence problem, especially in the middle Taiwan. Okay, so I think the data interpretation will be the very important issue for the next step. So here in this chapter, I would like to talk about of course, the data mutation. And I would like to introduce the criteria, the concept of the criteria, and using a Earth stand as the example. So before we started, I have several questions for you. Again, what is your monitoring purpose? Why you trying to put the sensor on this specified location? Why? What are you looking for? Okay. And what are you not looking for? So here, I have some questions for you because we need to go back to the failure mode from your answer or from your answers. And if you try to define your failure mode and have some of the pre-warning, early warning, so what is your criteria and what is your expectation? Okay, all the issues are included into the data interpretation. So I think we already, before we are going to inside of the data interpretation, I think we already talked about the filter. Oh, sorry. And also some of the data picking we need to use and done before the data mutation. Okay. So I think here we just show you some of the principle. If you already have some of the very apparent outlier, you need to pick up for this kind of the outlier data. For this kind, this data should be the outlier. Okay, so you need to remove. Okay, or otherwise you may have a interpretation for this kind of the data. Okay, so in the next, I would like to show you how to decide to for the data picking. We can use some of the plot and the comparison between the different data. So again, the questions, what is your monitoring purpose? This purpose should be related to your potential failure mode on your target. So for the Earth stand as an example, next time we are talking about the piping will be a very important failure mode of the Earth stand. Okay, because if you have a piping means that you have a pass inside of the Earth stand, and this pass will larger and larger, so some of the soil will lose and have a very big hole and a very dangerous pass inside of the Earth stand. Okay, so how to prevent the piping problem? Okay, if you already know that the mechanism of the piping, so what are you looking for this kind of the piping as a potential failure mode? So maybe you need to monitoring the flow condition inside of the Earth stand, and also maybe some of the leakage outside of the Earth stand. Because I say you never can stop the water flow of using a Earth stand. Always leakage, water leakage. But you need to find this leakage, the volume change quickly or not. Okay. and see if there's any sediment inside of this leakage water. Okay, supposedly if you have a very good condition and the filter for the leakage, the water flow should be clean without any soil particle. But however, if you already find that the earth stem with the leakage and this leakage is with some of the soil particle, means that maybe we have the piping problem. As I said, a pass inside of the earth stem, and this pass already have the scour and the erosion of the internal soil. Okay, so this will be the problem. And also we need to check the water pressure. Just as I said, here, we may check the different location of the water pressure to make sure that this kind of the water level, underground water level, keep constant. Otherwise, if you have a rising of the water pressure, means that I have the not pass of the leakage. So it is very dangerous. Okay, and also we need to check the length, the subsidence of the dam, because if I have a the piping inside of this earth dam, so I already have the internal erosion. So maybe the earth dam understand the potential failure mode first. So I would like to say this is the basic of the monitoring. Based on this, you will know where is the location I need to put the sensor, and what kind of the message I need to look at. So here, this is I think the demonstration showing like the subsidence. So this is the original elevation here, and here this is the then subsidence because of the maybe of the piping or the leakage, internal erosion. Okay. So in this chapter, I would like to show you some of the methods to let you understand if you already capture this kind of the data, how can you decide the situation is good or not? So criteria, how do you define a criteria? So here we have two methods. One is qualitative method, and the other one is the quantitative method. I think you already know that of this. So the qualitative method, we use some of the index, stability, correlation, rationality, consistency, mutation, and the symmetry. Okay, I think in the first step of the qualitative method, you need to have a very detail of the the calculation or some of the program processing. Okay, you just need to know that the index for this, maybe this 6 index for the first judgment of the criteria. But I would like to say the qualitative also easy to do, but it is limited only for the trend analysis. Okay, and the second one is the quantitative method. So we need the numbers. Okay, we need the number. to know that the condition is good or not. So here we will show you the theoretical, statistic, and illustrative mixing empirical in the final. So what is the qualitative method? Okay, here I would like to show you the first four index. Stability first. Sorry, because this is the true data from the Taiwan reservoir, so the mostly in Chinese, but I would like to show you. This is the pore water pressure. Okay, and this is the water level behind the reservoir. So what does that mean? If I have the earth stand and I have the water level, this is the water level. And I just say I have the flow pass inside of this earth stand. So this may be the pore water pressure. Okay. So I would like to say, based on the stability index, if I have the constant of the water level, the water pressure actually should be constant also as well, right? So here, this is a normal. Here, maybe this is a normal situation. Okay. Okay. So this is the stability. Stability. Okay. Okay. And I would like to say, if here, if the water level change with the time, so of course, if I have a lower water level, should I have a lower water pressure? Okay, so it is what we call the correlation, because this is the have a connection. So when I have the water level change, of course, the water pressure should change correspondingly. Okay, but you can find this is the linear correlation. If you have a nonlinear correlation, for example, of course, there's maybe some of the problem. Okay, so this is the example of the correlation. And the third one is the consistency. I would like to say, if you have the P1, but I mean that because this is the cross section. But if you already have a same position in a one is near my location, the other one is far my location, vertical to this cross section. Actually, these two water pressure should be the same because there's in the same location, but just in a different horizontal position. But actually, they have the same water pressure. So for this kind of the sensor, if you have the same, so same trend, so you need to have a consistency at all. And some of, I would like to say, the other consistency should be like this one. For the P1, P2, P3, supposedly the P1 is the largest, P2 middle, and the P3 the smallest one. Okay, so this is also the idea of the consistency. Okay, and the first one I would like to say mutation will be like the outlier. Okay, this is the time, and maybe this is the deformation of the earth stem. Sorry, deformation. Okay, so actually maybe we have a very smooth deformation with the time change like this one. But however, if you already find this, there will be some of the what we call the outlier. But this kind of the outlier will have two explanations. One, real one, because of the earthquake or something else. The second, because of the noise or the malfunction of the system. So you need to identify this kind of the outlier or mutation is real because of what? Okay, because of the system malfunction, or it is because of the some of the factor like the rainfall or the earthquake. Okay, so you need to identify first of this kind of the mutation. Symmetry. Okay, so symmetry will be some kind of the I would like to say how can I say this kind of the water flow. Okay, so symmetry will should be like this. Okay, so if I change with the water flow, P1 and P2 should be changed with the same pattern. Okay, with the same pattern. Okay, the water level should be changed to the same pattern. Okay, so so for this is the P1 and this is the P2 and this is the time. Okay, so should we have the same pattern with the time? Okay, so this is a symmetry. Okay, and another example is here. For example, this is the leakage, and this is the time. And also, I think this is the water level. So you can find this is symmetry with that, with the change of the water level. So I have the higher increase of the leakage. Okay, depends on your water level. So the leakage and the water level have the same pattern. And also this is the same. For here, this is the 1 year. And for here, maybe this is a 10 year. So you can find the change of the reservoir in a different season. So this is a leakage change with the water level. Okay, so this is a symmetry. Okay, right now, can you understand the basics of the what we call the qualitative method? Okay, because you don't need to quantify the value of the observation. You just check the behavior, the trend between the different kind of the sensor. But of course, you need to understand the basic failure mode of the earth stem first, because we use the earth stem for the example. So this is the qualitative method. And the next, I would like to show you the other one is the quantitative method. So the first one and the second one will be the theoretic and the statistic. Okay. Theoretic one, I think we already show you from the beginning of the signal and the system. If you already know that the parameter of the system, and you already know that the input system, so actually you need to know that the output. So for example, here I already know that all the parameter of this building. So when I have an earthquake as the input, I should know that the variation of the deformation of this building, okay, or the vibration of this building, because I already know that you can estimate the vibration or the deformation from your engineering structure analysis, right? So I think a theoretical one has the same idea. If you already know that the parameter of this, maybe the earth stem, you already know that the earth stem, and you already know that the water level. So can you predict the underground water level? You already know that the input, you already know that the earth stem, the parameter. So actually, maybe we can solve and predict the underground level because of the basics of the soil mechanics theory, right? So this is what we call the theoretical one. You can have a model or simulation if you already know like the parameter and also some of the boundary and the initial conditions. Okay, but I would like to say for the artificial material like the concrete or the cement or the pavement, this is the well-known the material we can understand. Okay, but however, for the slope and the earth stem, some of the ground material property we can fully understand that. Okay, so of course, if I cannot fully understand with the system, so there may be some of the uncertainty because of the unknown parameter. Okay, so here the theoretical the limitation of the theoretical method, you need to access all the parameters first of this system. Okay, and of course you need to access all the boundary and the initial condition, so then you can simulate and have a forward model to predict the behavior. So this is a theoretical method. But somehow I would like to say for the geotechnical application, it is hard to find all the parameters. So I would like to say most we use the statistic method to quantify the data and find the criteria for the early warning. Okay, and here is some of the illustrative method. Okay, I would like to show you in the next, and we can mix the theoretical and the statistic and also the illustrative method together. Okay, should be much flexible, but I would like to say if you combine several methods together, you need to think about more. And finally, it is the empirical method with the quantified data. But I would like to say This will be case by case. This is not a universal solution for all. Using the empirical data, it just can be used for the case. So here, I would like to show you the case study from the Yutan. The Yutan, maybe later I will show you the picture. Okay, I find some of the picture for you. The Yutan 水库。Okay, it is located in the between the Miaoli and the Taichung city. Okay, here, the location of the Liyutan 水库, Liyutan Reservoir, and it is very special. Let me show you the picture. Here, this is the spillway of the Liyutan Reservoir. Okay, and this is the reservoir area of the Yutan. And very unique, you can find the spillway is made of this kind of the shape, tooth shape, okay? And this is the natural overflow design, okay? There is no gate. I mean, you don't need to control the gate. You just let the water naturally overflow from this spillway. And this is the after pool of the reservoir, the Yutan. Okay. So I would like to say here, this is the actual data from the Yutan reservoir. So the first one of this dam safety interpretation, I would like to say, I trying to monitoring the seepage. I mean the flow, the volume of the leakage, and also the pore water pressure. Okay, against to the water level and also the rainfall, because I'm trying to quantify the relationship between the seepage or the pressure with the water level and the rainfall. Okay, because I want to understand the behavior of the seepage, And if I have a big problem of the seepage, I would like to extend to the phase 2, the horizontal displacement and the subsidence, and also the inclinometer inside of the earth stem, inside of this earth stem. So I would like to show you that the seepage versus the leakage. Okay, every earth stem have a seepage, and you can find some of the leakage finally. Okay, but I would like to say this is the normal condition. Okay, so I think you already know that if I have the water level, I have a seepage close to the reservoir, and maybe some of the seepage maybe from the basement of this earth stem, So this is the picture of this earth stem. Fine. And this is the leakage. leakage volume. Okay. So which one is safe? A, B, C. If this is the time and this is the volume of the leakage with the same level, water level, under the same water level. So I would like to ask all of you, A, B, C, which one is safe and which one is dangerous? If you already capture this kind of the data. A will be safe. B will be safe. Really? And which one is much dangerous? C. Okay. Okay. I think maybe most of you will say C is dangerous. Okay. And but I've heard some of the opinion that B is much safe, right? Right? Again, think about it. The same water level, and this is the seepage underground. I have measured the water pressure. So I would like to say, based on the qualitative idea, here I would like to say A should be much stable because there is no change of the water level. So supposedly there should be not a change in the pore water pressure. Okay, if this seepage path keep constant always. But you already know that if I have a higher water pressure means that maybe I have a higher seepage path underground. So yes, this may be much dangerous. But how about the B case? Why? Why it is decreased with the time? Why?
Yeah, there's some piping, and so the water flows out and the pressure lowers.
Yeah, there may be one of the good reason. And maybe this instrument getting died because some of the malfunction, okay? Or otherwise, maybe some of the past, the seepage path stop. Okay, so we need to understand, because I would like to say, if you have the constant water level, should I have the constant response? Because just I say, input the same, the system the same, so the output should be the same. Okay. If I have the same input but with the different output, there's only one reason: the system change. The system change. Okay. Okay. So please notice that why the seepage decrease. Okay, and increase. You already may understand that maybe because of the piping or other reasons. And there's another relationship between the water level and also the leakage. Here, in the previous qualitative, we just trying to capture the pattern. But in the quantitative, we are trying to capture the value, okay, and also the real relationship between the water level and also the leakage. So actually, if we, this is the theoretical one, linear relationship between the water level. Oops. Between the water level and also the leakage of volume. Okay, actually, we may have a little bit unlinear based on the observations. Okay, so you may have several data here, like this. In the right side, this is the real data from the Yutan reservoir. So this is the relationship between the leakage volume and also the water level. So you may find a relationship a little bit linear in the beginning and upward in the a high reservoir water level. Okay, but if you already have this kind of the data, but somehow someday, if you have a typhoon event, and I already find some of the data like this one. Several data here. So I would like to say this is might be a problem compared to the previous relationship, right? Okay, so please, this is the very important because if you can quantify the relationship, so you can quantify a criteria. Okay, I would like to return to the theoretical one. This is the flow net. Never learned before. No. No. Anyone? Only you. And okay. I think in soil mechanics, we already show you that the flow net method because if you already know that the gradient of the water flow, you may plot the path. This is what we call the flow line, and the vertical one is the gradient one. Okay, gradient. Okay, so if you already know that, for example, I just have a very quick understanding for you. If you already know that the difference between these two, H1 and the H2, so actually we can use the flow net method to plot. Oh, sorry. This is a flow line, okay, and maybe this is the gradient line, okay, because the change of the water level gradient. Okay, so actually, if you already, but I would like to say this depends on the K. What is the K? This is the hydraulic conductivity of the soil, means that the transportation velocity of the water inside of the soil. So you need to understand the K, the velocity, transport velocity of the water inside of the soil. And then we can determine how much of the water volume for the leakage. So this is I think this equation is very famous. What is that equation? The name of this equation? 我们叫这个叫什么 equation？ 忘记了，我有点 I forgot the name of this equation. But the Q is the volume of the leakage, and the K is the hydraulic conductivity. And this I means that the difference of this H1 and H2 means the difference of this hydraulic gradient. And the A is the area of this cross section. So if you already know that the basics of this parameter, we can estimate the Q from the theoretic theory. Okay, I would like to say, however, because some of the parameter you cannot find very easily, because I would like to say, inside of the core, we have a K1. Outside of the core, we may have a K2. And if you have a different material, maybe you have a different K, I mean the hydraulic conductivity of the soil. So right now, we would like to use the numerical simulation to predict if I have the water level, how much of the volume of the leakage can we estimate. And also this is another one. This is the flow. So we can use the numerical simulation to get the full problem and get the result of this Q. So maybe we can plot a Q. This is the leakage. Oh, sorry. And also this is the water level. We can estimate a theoretical one like this. Okay. So here, this is an example from the Yutan. Okay, and this result is from the flag, like the list. This is the flag. Okay, and this is maybe from the SIP. So we can estimate the theoretical one. And this will be the criteria for the monitoring, for the monitoring. Okay, so I would like to say here, this is the real data. This is the real data. And sometimes we can compare with the theoretical one. But however, then next I would like to say the envelope, the illustrative method with the envelope. Okay, because we may have a sum of the deviation. And here, this is another comparison between the seepage and also the rainfall. Okay, right now we have the Q like this. Sorry. And with the time, this is the time. Okay, so you can find the upper blue bar. This is the rainfall in each year data. And the pink one is the water level of the reservoir. And the purple one is the volume of the seepage or the leakage. Okay, so you can find this is the time history. I mean, actually, you can get this data if you already installed the sensor by yourself. But based on this time history data, how can you find there is normal or abnormal or dangerous for this earth dam? How can you judge? How can you interpret it? So here, actually, the same. We are trying to compare with the water level and the Q, the leakage volume. But you can find we advanced divided the data into the dry season without the rainfall. Without the rainfall. Because I would like to say, it is not so easy to plug in. Please look here. supposedly right now we are talking about the flow net, and we may have the seepage test. So actually, we can estimate the Q with the water level, right? But somehow, in the practice, it is not so easy because here we can collect the water flow inside of the earth dam. But however, if I have the rainfall, maybe some of the surface runoff okay, actually here, this is the Q2, and this is the surface runoff. So for this Q, maybe the summation of the Q1 and Q2. In practice, we may have this kind of the problem. So for this example, they're trying to exclusive the effect of this Q1. So they try to monitoring the data in the dry season without the rainfall effect. So maybe we can get the regression line because of the actually the Q2, the contribution from the Q2. Okay. And here, this is the effect combine the Q1 and the Q2 in the rainfall season. Again, this is the water level, and this is the Q, the summation between the seepage flow and the runoff, surface runoff due to the rainfall. So, because this is a lot of variation here, you can find. Because depends on the rainfall effect. So how can we determine the criteria for this kind of the variation data? We may need an envelope. To make sure that all the data should be inside of this envelope, and we think about it is maybe safe because of the based on the statistic data and illustrative envelope. But you can find here, there's a data, abnormal data, because this data is observed from the GG earthquake 20 years ago. Okay, so I would like to say, if you have some of the abnormal data, that outlier outside of the envelope, you need to notice, and maybe this is due to the some of the very big event like the earthquake, or the biggest rainfall typhoon event ever. Okay, so this is just the same. Okay, so I would like to say this is the water level, this is the Q, and this is from the seepage method and the flag and the seep simulation. So we already predict the value like this. But actually, this is the statistic. So actually, when I have a water level about the 300 meter, maybe I have only Q, only 109 or 120, 120. Okay, and this is the envelope. So here, the opposite envelope we define into the 320. Again, I would like to say here, we just talking about the relationship between the water level and the volume of the leakage. Also, you can apply the same idea to the what? To the water level and also the pressure, pore water pressure. Here you can find this is the location of the water pressure. This is the location of the water pressure. So if you already know that the seepage path, you should understand the difference between the sensor in the different location. So for the upstream here, this is the purple one. You can find the water pressure is much similar with the water level because it's close to the upstream part. But in the downstream part, green should be in a constant because we already have the seepage flow. Okay. So here you can find the pressure in the upstream is totally the same with the water level. But here again, this here, center here, downstream here. In the downstream should be much stable because of the core. So we may interpret this kind of the data because of we already know that the behavior. So you can have this water level with the water pressure, and you can get the regression line and also of the standard deviation. So next time, if you have a new record and a new observation, you can check this data is still in the relationship between the water level and the pressure or not. And you can tell why, okay? And I also try to explain the rest. For example, this is the inclinometer data inside of the reservoir here. So you already know that in a previous homework, the inclinometer. So with the time, you can find a change of the displacement. With the time, you can find this is the subsidence or subsidence measurement. So here you can find this is the real data. Why? In this time we have a big difference of the land subsidence because this is the time of the GG earthquake, the 1999 at the 1999. Okay, so for this I would like to say it is very easy for you don't need a quantified data, you just look at the trend, right? So you can have a very quick interpretation of the land subsidence because of this drop, So maybe we call this a mutation or mutation problem. Okay, here, this is the detail of the inclinometer. After the GG earthquake, here you can find a big difference of this deformation. Okay, and also here, okay, and this is the upstream, and this is the other side is the downstream. This is the real data. Okay, so you can understand, wow, it is very easy for your quick understanding of the behavior of the earth stem. And also this is the real data from this. I just plot in a cross section with a different day. So actually, this is the service, and I have a measurement with the subsidence in each year. So here, a very big drop because of the earthquake, GG earthquake. So this is the main location of the land subsidence, maybe more than the 30 centimeter. Okay, So I would like to say here, we already talked about the seepage. So maybe you need to exclude the rainfall effect. You need to think about the water pressure correlated to the water level with the maybe statistic method. And also the deformation, you can use theory or the time history, okay? And somehow you can predict because of the great event like the earthquake in the GG earthquake, okay? Or the rainfall in the 2000, this is 2009, 2009, okay? And I would like to say this criteria should be updated with the time. Should be upgraded with the time, especially you already have the great event. So you can examine the envelope still works or not. You need to update it. Okay. And also, I already talked about this. And here, this is just the table I would like to show you from the landslide movement. Sorry. This is the velocity movement. Okay. So this is the date. This is the month. Okay. So if you already have the velocity more than the 20 millimeters per day, it should be dangerous. This is from the Japan suggestions. Okay, so this is just for your reference. And in Taiwan, we also have some of the reference of the landslide from the 1999. But sorry, this is in the Chinese, but I think it's just for the reference to talk about if you already know that the velocity. I mean, this is the time, and this is your deformation, and you already know that. So you can calculate the velocity. So here, low velocity, higher velocity, dangerous. So you can use this kind of the velocity to check the stability of the slope. Okay, using the point of view of the sliding velocity. Okay, 1 minute left. I would like to show you there's some of the advanced signal. I mean the data interpretation method like the I scale or the catastrophic model. But I will quickly show you the end. Okay, this is us scaled originally for the river level variation, but right now it is in the starts, okay, prediction. And also here in these 5 years, we are talking about the AI, artificial intelligence, or the machine learning. Okay, so if you already have the data, can you predict with the AI or the machine learning? Right now, I'm doing some of the jobs for the data interpretation. Okay, but I would like to say, if you try to use the AI or the machine learning, always you need to remember that you need a good and enough data for the training, because I know that I should know that the data before I predict. Okay, so this is the basics. That's why I encourage you to have the good understanding of the monitoring, okay, before the analysis. Any questions? So in the next week, Friday night, we will have a midterm exam. So prepare to the chapter 3, and you can bring your own computer and a laptop. It is an open book exam. Okay, from the what is the time? I'm sorry, 6 to 8. Okay.
What the topic about?
Huh?
What the topic I mean? Visual. write something or maybe write code or
Yes, maybe there's some of the questions you need to use in the MATLAB to process.
We need a business.
No. Okay, see you next week. Bye.